Hello, it's James from XRobots.co.uk. This is part 1 of my bipedal Star Wars power droid project. Last week I attempted to finish the Hulkbuster project, or at least well enough that I can exhibit it. It probably won't be the last episode ever. I at least have one to go and test the whole suit at an event, and I may revisit it for occasional things that need doing to it in the meantime, but in any case that won't be scheduled now every other Tuesday. So I still have Project Ultron, which is a main project, which is one of the Tuesday videos, and I now need a new project, and that's why I'm going to build this bipedal robot. I will be revisiting my BB-8 version 3 and my R6 droid, which you can see on my channel, so I will be adding the features onto those, the BB-8 smart panels and so on, and the rest of the bits of R6, but those are going to pop up on occasional Fridays as well. So I want another project for Tuesdays, which isn't a massive project the last 2 years, but it's something I can develop technology for, which I can then use for future projects as well. So I've decided I quite like to build a two-legged walking robot, and I've got some of the previous ones I built in the past here, and in fact the reason for the XRobots website, which I registered in around 2004 or 2005, long before I even had a YouTube account, was to actually put those projects on, and I tried to build walking robots before with varying degrees of success. And I think with the work I've done on stabilisation with inertial measurement units on BB-8, some of the mechanical design that I've done, certainly with 3D printing, only one of these is 3D printed, and this is Android 12, so there were quite a few before that made of wood and other materials. I think obviously I can build something much better than I could before. So I've decided to build a character that's pretty well known. It's not too complicated because it's mainly a walking box, and that is a Star Wars GNK, Gonk or power droid. So I've knocked up this quick sketch in Autodesk 123D Design. It's basically a walking box, and you can see these things in the background in Star Wars when they're loading X-Wings and things, and these little droids are walking around in the background. And obviously they are generally a person in a suit walking round. They're about 3 feet tall. A lot of people make costumes out of 2 of those stacking plastic boxes put on top of each other, and some dryer, washer dryer hoses for venting steam on legs, and they put a child inside or something, and you see them walking around at events. And my plan is to make a real walking one, and the reason I've chosen this character, there are others I'd considered, including C-3PO and some other of the great droids in episode 7 that you see in Maz's Palace. The reason I've chosen this one is it's quite simple. Obviously it's a box on legs, there's no arms and other features to deal with, so I can really concentrate on making the legs work, and then if I can make it work well I can scale it up, and then I can do some other characters in the future. Possibly even Ultron, although it's unlikely to get legs, which is why I want to do a separate leg project, because the Ultron torso is already quite heavy and has specific features, so check out that series, especially part 1, if you want to know what that's about. I just wanted to show you some of my previous attempts, because I have made things that locomote on 2 legs, and one of the best walkers I made was Android 11, which we'll have a closer look at the actual thing in a moment. But here's a video, and this was back in 2012, so quite a while ago. I'm just going to set this thing going here. So basically it can walk pretty well. I used some dynamic stability using RC heading gyros, which wasn't ideal, but worked okay I guess, and it did walk along on 2 legs. And it is dynamically stable, so it is actually measuring the angle and adjusting itself as it goes. So yeah, we'll just watch that walk up and down a bit. This is a similar style to what I'm going to build for the GNK droid, so hopefully a bit bigger than this though. Let's just find the other shot where it walks away from us, because here we go. You have to excuse the stuff in the background. This is before I did YouTube properly. There's lots of other stuff in my house, but there we go. So that's a bit of side-to-side wobble. Not the best, probably mechanical design, or at least the mass is in the wrong place. But it walks not too badly, the steps aren't too big, but there we go. Next up is Android 7, and we're going back here, the video I uploaded in September 2007, which was 9 years ago. Although actually I made this long before that. I think this is one of my first YouTube videos once I got an account. I previously hosted this on my website. Now in the right hand corner here you can see a bed. This is in a room in a house share I used to live in, and this is a workbench behind a bed sheet hanging up. So this thing is about 5 feet tall, and it's made of wood, mostly pine and plywood painted silver, and it's all strung up with bungee cord, and it's using 3 wiper motors to walk along, which are kind of hidden in the hips there, and the thing on its chest is a plastic dinner plate. So yeah, it does walk. It didn't really even have a microcontroller on it. It's also powered by mains outlet power, which is what that cable is dragging behind it, and it had a PC power supply on board powered by the mains. But it does hobble along. The idea was to make it passively dynamically stable by having bungees and things and various cords to dampen and sort of restrict its motion, a bit like mechanical suspension. There are various other Androids, basically about 10 different ones on my website. If you go and have a look and drop down on the drop down for all projects and have a look for those older Android projects. We're now going to jump forward though to 2013, so about 3 years ago. And this is Android 12. We're going to have a closer look at that in a moment, but it doesn't work anymore, so here's the testing video. So it wasn't too bad. There's reasons why this works less well than Android 11, which was the one I showed you first, which worked pretty well, and why this is a bit drunk looking and doesn't really walk in a straight line. But it does nonetheless go along, sort of. It is again fairly dynamically stable, but again using RC heading gyros rather than a proper inertial measurement unit, and it doesn't have an Arduino in it. It's using a pickaxe, which is an educational system based on pick chips. So it kind of works. The actuators and the legs aren't really up to it, and it hasn't really got a clue what's going on for reasons I'll come on to shortly. But there we go, and you can find this in my channel if you look back through the old videos. So obviously, considering the past projects, I'm pretty sure I can make something probably this size, which works a lot better with the knowledge that I've got now, with a better mechanical design using a modern microcontroller like an Arduino and a proper inertial measurement unit. But let's have a closer look at the mechanics. So we're going to take a look at Android 11, and this is one of the ones that work the best, and in fact most of the ones that work the best worked in the same way mechanically. So what we've in fact got here, of course it's got 2 legs, but each leg is actually a kind of parallelogram arrangement with effectively 2 knees, and these legs make a square here. So there's basically a double hinged linkage, so a 4-bar link effectively, for top and bottom, and that means that basically the body always stays upright no matter what position the legs are in. Here's a little diagram. So this is basically the body, and then we've got these parallel things here, and obviously wherever the legs move it doesn't really matter because it always leaves, you know, whatever the foot on the ground there always leaves the ground level, it leaves this level, and it leaves this level, and it leaves this upright. So this is always a right angle, and the body's always upright. In order to actually balance and shift weight backwards and forwards, however, the body is actually on a hinge at the waist here. There's a piece of studding here, and at the top there's another servo. So in fact this thing will move in and out a little bit, and this had all the batteries and things mounted on it. So that meant it could throw this body backwards and forwards to help it balance. Also, of course, it needs to lean side to side, so there are a further set of axes about the ankles and the hips here, and those are able to, if I can just squeeze one, move the legs the other way, and also move the ankles so that it can get its feet flat on the ground or wherever it needs to be. The actuators in here are some fairly cheap radio control servos, and these are just pushing push rods across the parallelogram. So the servo front is right in the front here, and the rod goes across to the back, and that of course causes the parallelogram to offset as the servo moves. So if I just give that a shove there, you can see the servo horn will move one way or the other. It's a bit jammed, in fact that one's stripped. So yeah, that will cause the legs to move each side, and then on the hips and on the ankles, the other servos there push rods, so we've got a hinge here, and this rod pushes up and down. So as this servo rotates, it can offset those joints. I've removed the electronics from this now because I took most of it and put it onto Android 12, but the way this stayed stable was by using radio control heading gyros, and these are little units which you wire in line with a radio control servo, so your radio control servo signal goes into the gyro, the output goes to the servo, and then however you move that heading gyro basically will affect the servo signal and make it move to a different position. It adds an offset to it in either direction as you turn it, but only when you move it. So it's not a proper inertial measurement unit, it's got no accelerometer in it. It only has some output when it's in motion. And these are designed for quite small radio-controlled helicopters when the wind blows or something, to basically keep it in the right direction. So you'd use that to either offset your dual rotors or your tail rotor, depending on how it's designed, to keep it going straight. So those were quite cheap. I got them from Hobby King. I think they're about £10 each. And I had a lot of them wired in line with every servo. So basically I sent fixed positions on fixed timers to each servo. Every servo signal ran through its own heading gyro that were oriented correctly for the axis, and that then told the servo effectively to go to a different position or added an offset as this was in motion. And it just happened that basically there's not much tuning on these. You can adjust sensitivity, that's the only thing you can adjust, but it just so happens that those RC heading gyros matched the dynamics of this robot. I built it just the right size to move at the right speed. The signal variance that came out of these heading gyros kept it stable. And as I found when I tried to basically make the bigger Android 12, work in the same way, it didn't work very well at all because it needed to move more slowly. So those RC heading gyros with the response they had didn't really match the dynamics anymore. And here they are in fact on Android 12. So you'll notice there's 3 of them here, which are wired to 3 of the leg joints and their positions on different planes depending on which servo it is. So this will be the one for the side-to-side action of the hip, and these will be for the other 2 lower down the leg. There's also one in the middle on this one, which is for a main side-to-side axis, which affects timing of the steps, I think. But as I say, this Android moves a lot slower because it's bigger, and therefore the response rate of those gyros is too fast, which is why it occasionally gets stuck on one leg, looks like it's drunk, and obviously it doesn't compensate properly at all. The other thing to remember is that as we make something twice as big, we don't just need motors twice as strong, it doesn't use twice as much power. So if we take this cube here and we make it twice as big, so we're actually making it twice as big, twice as high, twice as wide and twice as deep. So it's getting twice as big in 3 dimensions. And that actually leaves us with a volume that's 8 times bigger than the one we started with. So taking my first Android 11 there, the little one, and then trying to make one twice as tall actually needs motors 8 times as strong. And if we then go twice as big again and make it human size, that needs again another, we multiply by 8 again. So from the original one, we need to multiply everything by 8, then multiply by 8 again. And if we want to make a Hulkbuster we can ride in that's 12 feet tall, we then have to multiply that by 8 again. So we end up with needing, actuators that are many, many times stronger than a very small model or a small Android. And that's why I'm sticking with one the size that I'm going to build it. I'm not going to try and make it human size yet, because basically our power to weight ratio, the strength of the motors, the strength of the batteries and everything gets much, much, much bigger, and they still have to be quite agile to balance. So that becomes a real problem. However, that was partially one of the mistakes that I made. So again, the actuators in this are actually radio control servos. So they are slightly stronger ones. Let's just have a look. You can see the backs of them there, but they're relatively tiny compared to the robots, the metal gears and stuff. And basically what I did was take those apart. They actually drive a belt drive which drives the actuators up and down. So you can probably just about see some belts in here, and these stainless steel runners, which are basically what you get in a 3D printer for the linear actuators. And I broke out the pots from them and put these slide pots on which measure the distance, and then the actuator arm pushes the joints up and down. I also really overcomplicated things by having a separate hip joint in the side plane here, which is at the back with this slider, one for the knee which is at the front here, which slides the knee joint, and then a separate one for the ankle down here. So that's the actual ankle joint, and that's another linear actuator there moving the ankle joint. So that meant that basically even a small deviation in the angle here affected quite badly the uprightness of the entire Android. So rather than having that parallelogram that always kept the body upright, it meant all of these servos have to work together instead of being able to isolate them and control them independently. So before, obviously, one servo moving would always mean the body was upright, but in this case every single one in the leg would affect that, and the others would have to compensate to keep it upright. And to make matters even worse, you can see there's no side-to-side axis in the front plane around the ankles. The bottoms are just curved, so this foot does not tilt. It can tilt side to side at the waist, however, and that's what this servo is here, which pushes a lever and there's a pivot point which is right in the pelvis. You can just see the end of the studding there that pivots it. So that's quite a big leverage angle that actually moves the hips side to side. So I'm pretty surprised that project worked at all, and obviously you can see there's issues with it walking, where one of them is controlling all of those joints to keep the body upright. The other one, of course, is the dynamic stability, with the compensation rate of those gyros being far too quick for the speed that the android's actually moving, which is why it gets stuck on one side and wobbles a bit, instead of it actually working at the same speed as the steps, which is what happened with the smaller android, because the smaller thing moves quicker. So needless to say, I'm pretty sure I can make something much better now if I stick with my parallelogram leg design, and that's the same design that Android 7 used, the big wooden silver one that was 5 feet tall, but obviously building it this size needs 8 times less power and 8 times less motor torque, 8 times less battery power. So it needs bigger actuators than this, but probably some average motors that I can control. So if I can control, the PID response for those motors moving to their positions, and I can use a modern microcontroller like an Arduino and a modern inertial measurement unit like the ones I've used in my BB-8 builds, then I should be able to tune that dynamic stability to work at the right speed for the dynamics of the robot. Then I should be onto something to actually make that work properly. Here's a whole bunch of motors. I got these from eBay from a Chinese seller. They arrived in a couple of weeks. It wasn't too bad. They cost about £8 each in money, and these are roughly 100 RPM 12 volt motors, and they have worm gears inside and some various other gears, so they're pretty tough and they won't backdrive. And this is my hand for size reference. They look pretty small, but they are actually the similar size motor to the ones I used in my R6 Droid to pull the legs straight and at an angle to do the 232 conversion. Now that version was geared down a lot more, but they're pretty tough basically. They're quite tiny really to pull that whole R2-D2 leg around at the hub. So have a look at that series if you haven't seen it. I'm not really even sure what the rated torque is on these. I generally like to test motors by powering them up and grabbing them, and having worked with a similar gearbox before, I know that pretty much this should have enough torque before I bought it. So if I just power this up, I've just got an 11.1 volt LiPo here, which is probably a bit flat, but anyway, let's just power that up. So you can see the sort of speed that that turns. It's fairly quick, but not too quick. And if I just grab it, you can hear the motor straining, but I can't stop that with my hand. So with a small enough gear on here, and it's not going to run the joint directly, it's going to have an actuator that's levered across the joints again. I'm pretty sure that should be fast enough and powerful enough for a robot of that size. This is one of the servos in Android 12, or a very similar one. It's actually a 15 kilogram torque servo, but look at the size of that. So the electric motor, of course, is in here and all the gearing. So, and I know it's a lot smaller than this one. So obviously this is actually quite a lot bigger and a lot tougher, and it won't backdrive because it's got a worm gear in as well, whereas this one hasn't. It's just spur gears. There's several approaches to building an actuator that's linear. So one of them, of course, is just to do what RC servos generally do, which is you have a kind of the output shaft of the motor there, say, and then you have a servo horn or a lever, another pivot, and then you push a rod that moves this way. But of course, that doesn't give you a linear response. So when the motor's in this position and the rod's coming off in that direction, this gives you a kind of acceleration. The fastest motion is when it's moving here, and it slows down again here on its rotary motion. And also this is putting much more load on the motor when the lever's right out than it is when it's over here, in terms of being back-driven and in terms of the motor driving the rod. What I actually did in Android 12 was to use one of these and put a kind of toothed pulley on it. So I actually had a belt drive with a pulley at each end, the motor on one end, a pulley that went all the way round. That was attached to a linear slider with a linear rail, and then I had a carriage that went up and down that had the output shaft on that then drove the Android. So as this turns around, draw the arrow bigger, this drives up and down, and that means as this rotates I get a constant speed and a constant force. The only downside, of course, is, well, the belt skipped sometimes. I could have used sprockets and chains or some other cord wrapped round multiple times and anchored, but also I had to build this whole linear slider assembly, and space is quite limited in the legs. What I'd like to do with these motors now is actually build more of a rack and pinion assembly, so basically having a gear here on the motor and then having a track with teeth on that drives up and down, and that means I can make this much more compact. So probably we need a couple of little wheels that keep the track pressed against the pulley, but this can ride up and down, and I don't need to build, you know, a pulley with a belt and another pulley at the other end or any track assembly. It can just be this, and this pushes across the parallelogram. It struck me as well I could build that slightly differently so that the motor floats in the middle with the track, 2 tracks in fact, and one would push that way and one would push that way as the gear turns, and it pushes those in opposite directions so that the motor could float in the middle. Then I'd have 2 of these which push out either side. This would also move, of course, twice as fast, although I could just put a gear twice as big on here to get the same result of the single-sided one. That's another reason why I've chosen a motor like this with a worm gear, so the motor is facing this way, it has a worm gear, then turns around the motion, and all the other spur gears face this way till they get to the output shaft. These are the motors, or very similar to these, I used in Ultron, which of course is in line. So this is much wider this way from the output shaft. So if I want to build a linear actuator with a rack and pinion, then of course my track or my rack will slide this way, which keeps this profile very thin. Obviously if I was doing that with this motor, then this thing gets much wider this way, so this is going to be much harder to fit in the leg than this, which is comparatively skinny. The linear actuators will work well to push across that parallelogram on the side plane of the legs, but then looking from the front we've also got to move the ankles here and the hips as well in that same kind of rotary motion, so there's probably less space in here. We could put linear actuators down the sides here, which is sort of how I did it before, or they could come from the top of course if I bring this right up into the body, but there's probably less space for that. So there's another approach we could take for that, which is simply just to put a very big gear onto the foot. So if, say, that's the foot, have a kind of gear there with its center point, in fact there, that's a gear, and then just run a smaller gear on the motor around that way so that that can pivot the bottom of the foot side to side, and the same with the hips. Now there's much less travel in this side to side than there is in the other joints, so we might get away with that with a small enough gear, or again we could just use a linear actuator across the joint. We really have to scale this thing out and see how small I can make those actuators. Hopefully that's enough information to convince you that I can make this work. I've certainly talked myself into it. If you like robotics projects, then coming back next Tuesday will be the continuation of Project Ultron, hopefully working my way up partially to the head at least. So don't forget to subscribe for more updates on this project, which will be in another 2 weeks, and other projects, and also check out the social media links in the description to this video.